1, 2, 3, 4, he said n. N is what? How
So
many?
it's Bernoulli triangles, right? Each n is a Bernoulli triangle. Either you get it or you don't.
Any triangle is a Bernoulli triangle, exactly. And Bernoulli is exactly the name we will give to this event, exactly. So what is n? That's my question. How large can be this experiment? Infinite.
Any number. You can take any natural number.
It can take, it's unbounded, right? We will say, okay, this is going to happen with a probability which is decreasing exponentially. It's going to be super ridiculously small probability, but there is no reason to bound theoretically the number of throwaways that you will need. You may say 1,000. There is a non-zero probability of getting 1,000 plus 1. Or 1,000,000 throwaways. There is a non-zero probability to find 1,000,000 plus 1. And this is the idea of unlimited support. This is a discrete random variable, but it's a bounding. Remember, we discussed that last week. Even if it has an infinite number of elements, because we can count them, because it's a countable support, this is still a discrete random variable. And it has an expectation. You will play this game, you have nothing to lose, you can only gain something. The question is how much. So we can make a positive expectation. This game, playing this game, will bring you money. The question is that we don't know how much. We can define the expectation, and remember the expectation of this variable will be the sum of the potential outcomes, which is this column, weighted by the probabilities of those outcomes, which is this probabilities in this column. So this is the sum from, let's say, e equal 1 to infinity, because the number of outcomes can be infinite. The prices are 2 to the power 5. For 1 is 2, for 2 is 4. So you see how we are taking those exponentially increasing prices. And this is weighted by probabilities, which is 1 over 2 to the power 5. So you see what happens. The game is designed in such a way that even though probabilities are increasing exponentially fast, geometrically fast, the gains are increasing at the same rate. So this is the sum of I that will give you an infinity. So this is an example, a theoretical example, a historical example, by the way, in which we find a game with infinite expectation, with unbounded expectation, not well-defined expectation. Participating in this game, literally, can make you reach beyond any unthinkable level. And the question, the paradox comes when this guy presented this game to the people, to the Russians, and said, okay, there's nothing to lose for you, so this is a right. And in order to play this game that can only bring you good things, you will have to pay a fee, and that's fair. How much you will be willing to pay in order to participate in this game? Sorry, I will try, give me just one more week. And still I'm sort of putting faces and names. One more week, and this week we will check if I did the homework right. How much would you willing to pay for participating in a game like this? You have nothing to lose, so it's fair for me to ask you some money.
Not very much.
How much?
How much is one round of this game?
How much is what, sorry?
Oh, one round. Like
One round, the first round?
yeah, just first
Two.
round. Two.
You just, the first time you get the head, I give you 2 euros.
Maybe I just participate 2 times, so that's 4 euros.
You spend like 4 euros.
Yeah.
Rationally, I'm willing to pay infinity or less.
You will rationally pay?
Infinity or less.
Of course,
Yeah.
that's for sure.
Infinity.
Isaac, right?
Yes.
That's for sure. You will not pay more than infinity. But the question is, how much you will be willing to pay? You cannot pay negative. How much?
Since I'm expecting infinity.
You are expecting infinity,
I'm
literally.
willing to pay infinity.
That should be the rational answer.
Yes.
But for instance, according to this logic, she's not rational.
Yes.
This is the shocking thing for Bernoulli, for Nicolas. He was shocked about that. She's paying a super conservative amount, Angel.
1 per game.
One per game, how much? You just, we get the coin, you will start.
Each time I toss, I pay 1.
No. So you tell me how many, then you will be like Isaac.
Exactly.
You spend an infinite number of times.
Yes,
You
sir.
pay, you will be willing to pay infinite.
Yeah, up to
Sure?
up to 1 per game.
Okay,
Yeah.
we participate. You are willing to pay infinite, I give you cheap, give me 1,000.
No, I mean,
No, why not? You told me infinite.
Yeah, I
So
mean,
how much
mathematically
they-
makes sense.
No, how much you will pay right now, right here, to participate in this game? Not theoretically. You tell me infinite, I'm gonna give you the offer of your life, 100 euros. You will be super happy. How much? Angel? Not infinite. No one will say infinite. But the problem is not even 1,000. People always thinking in terms of ridiculously small amounts, like
But,
4, 2.
but actually, I wouldn't even pay that much because it would be like
So how much, Angel?
3 or 4. Let's
3
say
or 4?
No, it can never, sorry.
It's very a question because I don't understand.
How much, Natalia?
It's like you, depending on the amount you pay, you toss more times the
No,
coin.
you
So
just
I pay 2.
participate.
Ah,
You
then-
participate,
then-
and no, it's not like any time, no. Ex ante, you want to participate, you give me some money.
Plus 2. I pay 2.
Just 2 euros, but you see the paradox. 4 euros is the most I'm getting out of an expectation of infinite.
Yeah.
So this guy was shocked, because this is what you are feeling right here, is what Russians 300 years ago were feeling like. And this is shock mathematical, it's nonsense. So how is it possible? They don't realize what the potential gains. It's an infinite expectation. You may get billions anytime you get the tails, you are exponentially increasing the price. And it's like your brain refuses to accept the idea.
But also, for example, there is no incentive to pay more because it's like the one that pays the most is the one who plays.
Will be okay.
That
Put
makes
it,
sense.
let's put it in economic terms. What is the maximum amount you will be willing to pay?
Let's say 40 for
40.
saying something.
You want to pay 40?
I mean, if the gains are exponentially infinite, yes.
This is the structure of the game. There is no trick here. That's the mathematical structure. And he was shocked by finding people in this order: 2 euros, 3 euros, 4, 5, 6 at most. And he says, it makes no sense. Why? What is this thing? And he writes a letter to his cousin, who is a better mathematician. And the other better mathematician is Daniel Bernoulli, the one that we mentioned before. And it takes like 20 years to Daniel Bernoulli to figure out the answer. So the problem is complicated, but it takes like 30 years to find the solution to Bernoulli. In 1738, there is another Swiss guy that in parallel figure out the solution, Kramer. This is another mathematician, maybe you know it from the Kramer, Rao, bounds, and these sort of things. That Kramer finds out the solution a little bit earlier than Daniel, but this guy published first. And in science, this is like a sort of, well, you publish first, then you get the grade. So this is the first time it's published. In 1738, Daniel Bernoulli provides explanation for what is going on in this problem.
But that's a different Bernoulli, you say, right? Is this a different Bernoulli?
This is Daniel, his cousin. The other guy, he wrote the letter. It took all this time, right? So you see how things sometimes it happens, right? It's like 1713, he posted the problem, the riddle, and like 25 years later, this guy sort of figured out a sensible solution. And what he thinks is, the problem is that people don't think in terms of wealth. People must think in a different dimension, because otherwise we cannot sort of consider the problem. You think in terms of wealth, this is a paradox, because you should be willing to pay an infinite amount of money. Theoretically, okay, not infinite, but give me millions, the maximum you may pay. And this is very far away, it's very far from being that case. So he thinks it must be a different situation, people must think in a different plane, in a different scale. So he figured out something that nowadays he calls something in terms of felicity, something like that. He was the first person ever, a mathematician, that formalized the idea of utility function. It's not wealth. is something in your brain that transforms that wealth into something that we may call happiness or utility. And it's according to this scale with which you make your decisions. It's not wealth what matters to you, it's this happiness that wealth brings. And that's where we are going to find the solution. Why in your brain the information in that game has been reprocessed and translated into something different. And what he thinks is that, all right, how people perceive wealth. It is perceived in an increasing way. So this function, this kind of mystic function, first time ever figured out, must have a derivative that must be positive, must be an increasing function. Because everyone feels happier with wealth. The more wealth you give me, the happier I am. And this is pretty much for everyone. So this must be an increasing function. But at the same time, and this is super interesting, the second derivative of this function must be negative. Because happiness is greater when you have little wealth. If I am a poor guy and you give me 10 euros, I'm going to be super happy. But if you are Cristiano Ronaldo and you give me 1,000 euros for Cristiano Ronaldo, it feels like, oh, come on, I don't know even, bother myself. So people perceive wealth in different ways according to a function that must be increasing. So utility must have a positive derivative, but that derivative must have a second derivative that must be negative. So marginal, that utility must be increasing, but marginally decreasing. So he figured out something like this. That's how wealth must be mapped into your brain. Stylized. And this is, as I said, this is not probably literally like that. This is an economic model and a mathematical approximation to capture the most salient features of how our brain processes information. It has nothing to do with cultures, has nothing to do with religions. This is something that is intrinsic to us. It must be like a genetic program. We perceive life like this. We are happier with the more wealth you are given, but it has this kind of marginal decreasing effect. If you give me one beer on a sunny day, that first beer tastes wonderful, but after drinking 5 beers, the 6th beer is not okay. This is fact, right? No, we all have experienced this type of things. So this is the utility function, and he thinks, give me a mathematical example of that. That would be, for instance, the natural logarithm, a function that perfectly matches this behavior. So humans must make decisions based on a mathematical structure, if you like, similar to the natural logarithm. And he proposes the natural logarithm not just as an example. He really believed at that time it must be something logarithmic. It must be some kind of behavior like that. And it's capturing this phenomenon, the utility function. All right? So according to this structure, he can solve the riddle. All right? What I'm saying then is that you will not process information of the game in these terms, but make decisions based on the expected utility. Because wealth is random, the point is that because wealth is a random variable, the utility function that takes as an input that wealth is going to be a random variable itself. Remember, we discussed that last week. Randomness is such a powerful trait that anything that you do with a random variable is automatically a random variable itself. So if you map random wealth in your brain somehow, that mapping is going to be that of a random variable. Because you don't know how much wealth you have, you don't know how much utility, how much happiness is going to bring you. So you will not make decisions based on the expected value of wealth. You will make decisions based on the expected utility of that random wealth. And this is the whole point. 300 years ago, someone makes the foundation of modern economics. 300 years ago, a Swiss mathematician, not, almost philosophically. It's not like a proof, it's not like a likes that rigor, so we call it heuristic approximation. I think it may be like this. I don't have a proof. I don't even have, kind of empirical evidence supporting my theory. But it brings this kind of philosophy. It must be like that. It sort of agrees with this thing. It's not the expected wealth, but the expected utility. So we now can sort of solve the problem working in terms of the expected utility of that wealth. So we have price, it's random. Then we add a new column, which is utility of that price, right? So you will have the natural logarithm of 2, the natural logarithm of 4, the natural logarithm of 8, and the natural logarithm of 2 to the power of n. And this is the new random variable that is important for you. So it's not the expectation of the price, but the expectation of utility what matters. So we use the same thing. Probabilities have not changed. What changes is the values taken by this new random variable. But the expectation is defined according to the same principle. You want the expectation of this new random variable, you take the values taken by the random variable and make the sum weighted by the probabilities. So the expected value of the utility provided by this game would be the sum of the natural logarithm of 2 to the power of 5 times, right? You see how we have transformed the original outcome of the experiment, weighted, of course, with the same probabilities. This is going to be sum of I natural logarithm of 2 times weighted by 1 over 2 to the power of 5. And this guy here is not depending on the index, so we can take it out. This is like a natural logarithm of 2, the summation of I, 1 over 2 to the power of 5, and this thing converges to 2. It's no longer an infinite expectation, it's now converting to a fixed amount. This is 2. So the expected utility, the limit, when you allow this I going to infinity, the number of thrown is going to infinity, of the expected utility that we have defined will be the natural logarithm of 2, which is fixed, it's not changing, it's not depending on I, and this component here, that thing, in the limit, tends to 2. By the mathematical properties of the natural logarithm, this is the natural logarithm of 2 to the power of 2. And this is the natural logarithm of 4. And then he comes with something which is super interesting. Playing this game will give you the same expected utility as not playing at all and taking 4 euros certain, just like a Xiaojin. So we will say Xiaojin has a utility function, internally her internal utility function looks like a very natural logarithm. Of course, it's pure casualty, it's nothing, and it's not like that, believe me. But mathematically, it could be approached by the natural logarithm. C is willing to pay 4 euros. C will be equally happy if instead of letting her play in the game and get a random outcome, I gave her 4 euros right away. This amount, which makes this utility, so playing a game and getting some expectation, gives me exactly the same utility as certain fixed amount. This guy here plays a super important theoretical reference for us. This guy is going to be called the certainty equivalent. So when you are confronted with risk, we theoretically can do this approximation. I can remove the risk, giving you certain amount of money, that if you have a utility function like that, has this property. this omega star is going to be smaller than the expected value of your random wealth. Here we cannot appreciate it really in all its magnitude. We can say 4 is less than infinite, of course, but it is matching these circumstances. And if that happens, you are said to be risk averse. You dislike risk, and you dislike risk, and that's manifested in that you are willing to accept something certain, which is smaller than the expected gain from the game, from the random game. If that happens, you have a utility function which is like that. Stylized, right? You may tell me, but it needs to be stylized like that? No. Increasing, first derivative is positive, and marginally decreasing, that means second derivative that is negative. This is kind of the overall behavior of your internal way of processing random information. It's clear, guys? This concept for us is fundamental. We are not going to use it. It's a theoretical reference. It is telling me, is it possible to remove uncertainty? But if I want to remove uncertainty, and I'm dealing with a risk-averse individual, and risk-averse individual is the characteristic agent for us. Most people will be like that. Then this guy is willing to accept a smaller amount than the expectation of the game. And this amount is called the certainty equivalent. So theoretically, we can construct a theory building on this certainty equivalent. And we will do that in order to justify how we proceed when do valuation. The certainty equivalent is something that we cannot observe. I asked Xiaoyi, as he told me, 4. So I can infer something about her. But I need this answer. How much would you be willing to pay? How much are you willing to pay in order to participate? And many people will not, you see, I have some problem with Angel in order to sort of make this question clear and to get a right answer, right? Because it's kind of complicated, right? Why 4 and not 4.10? The certainty equivalent is kind of complex. People don't, we are too much used to think that, particularly in economics, of course, this is the basis of our field, that things can be quantified. Not everything can be quantified. How much you like chocolate? How much you love your mother? In a quantitative scale. And the answer will be, I don't know, a lot, or not too much. Yeah, but how much numerically? It cannot be, many things cannot be quantified. So we have trouble to work with the concept of the certainty equivalent, not theoretically, but in practice. So this certainty equivalent is going to be a theoretical reference for us. Okay? So this is the foundation of our utility function and our field, economics, 300 years ago. In this story, the next stop, so we jump like a 30 years, now we need to jump like a 250 years. We need to go to the end of the World War II, and we find a Hungarian mathematician, mastermind, brilliant, von Neumann, and a mediocre Austrian economist guy, Oskar Mollers. These guys formalize this concept. So what I'm giving you here, you say, what is the difference, right? These guys come and now talk about lotteries and utility and expected utility. What is this different from what Bernoulli did? Nothing. The point was Bernoulli, a mathematician, published a paper 300 years before in a kind of random journal in Latin. So these guys are not aware of that thing. They just, developed 300 years later a new sort of trend. They are discussing how decisions are made. There is the beginning of the computer science field where von Neumann is one of the fathers, and they are thinking how rationally things can be justified and constructed mathematically. And von Neumann, because it's really the theory of von Neumann. We say von Neumann Morgenstern, but really the father of this is von Neumann. And he thinks, there must be certain rationality in making the decisions, and we can sort of prove things mathematically. And this is the job that he does. The contribution of these guys is formalizing mathematically. Bernoulli puts the idea heuristically. It must be like that. but it lacks a kind of formal, statement. These guys make a logic construction and they prove, starting from simple axioms, they prove things. And this is the contribution of the von Neumann-Morgenstern theory. And this is what we call, right, the von Neumann maximizer, the utility maximizer. So the idea is that you consider a discrete random variable in which you may have a number of outcomes and each one has a probability pi, right? So for event x1, x2, xn, we have probabilities p1 up to pn. Then you have a utility, a guy that is endowed with a utility function. And what these guys prove, long story made short, is that there is a certain rationality in making your decisions by maximizing the expected utility. And this is what a computer would do. You could program a computer according to certain axiomatic laws, like if A is preferred to B and B is preferred to C, then A must be preferred to C. According to this type of logic, you will be an individual that makes decisions maximizing expected utility. And they sort of formalize the idea of Bernoulli 300 years ago by making this type of statements. So you pick up the expected utility as the basis for making decisions under uncertainty. And since 1950s, from the 50s nowadays, this is the basis of our theory. You will make individuals, you will consider individuals that maximize expected utility given constraints. And according to this theoretical background, we can prove a lot of different results in economics in different fields. And this is the basis. You've seen this in macro, you've seen this in finance, you see this in micro, because it's the basic way in which people make decisions according to our models. So, for instance, in the CAPM, which is a model that we will see in the chapter 2, and it's one of the most well-known, if not the most well-known model in finance, individuals make decisions maximizing an expected utility function, which depends, is called the mean variance. And the implicit assumption is a utility function which is quadratic. The theoretical justification of something like the CAPM that is deeply related to the mean variance setting can be justified either assuming that returns are normal, and we said something yesterday about the normality of returns, or assuming that individuals have a quadratic utility function. So it's not the logarithm, but it's quadratic. So it should be something like this. And of course, again, we will have something to say about these assumptions when we discuss the CAPM later in chapter 2. But the point here, something like the CAPM, which we explain nowadays in all the universities, in all masters in finance, we still explain the CAPM. This can be justified in terms of the expected utility paradigm. Okay? Alright guys, let me skip the workshop. I prefer teaching today the theory, and I will do these workshops in the next Friday. Next week we have classes on Friday. So let me skip that. If you want to try yourself about doing that thing with Excel, it's very simple. I'm trying to sort of consolidate these ideas and to keep showing you things how it can be done easily, financial modeling, using models and files. So here it's going to be a very simple idea. We have 3 lotteries. This is the notation, the terminology that von Neumann uses. And basically we have like a different payoffs. And we have like a 3 games or 3 lotteries or 3 assets, if you like, and in which those outcomes occur with certain probabilities. And we're gonna do things for 2 representative agents. One that is the one that matches the risk-averse individual and has a utility function that is increasing and has a second derivative negative. And we call this thing risk aversion. Or a different set of the utility function. So you make decisions according to a different set of preferences. And for a guy like this, which is linear, we call this guy the risk neutral guy. This is risk aversion. This is an example of risk aversion. This is an example of risk neutrality. And these guys when confronted with the same games, will make different decisions because they have different preferences. So for individual A, I don't know, lottery B is the best one. For the risk neutral guy, lottery C is the best one. So the game, we are gonna show that. We're gonna try Excel in order to solve this problem in a very simple way because we have the discrete context. Okay, but I prefer keep working today with the theory. All right. So the point is the expected utility.
The risk lover guy would have a utility function e to the x.
There is a third type of guy, a third type of preferences, which will be the risk lover. I'm going to discuss that, what is risk neutral, who is risk neutral, how the preferences of a risk lover look like, the risk neutral, and the risk adverse. Pretty much in this theory, the three type of preferences that we have. According to this system, according to this theory, and it's a theory, you may tell them, it's just like that. Well, we have evidence that people could make decisions based on other, in different paradigms. But this was like at the beginning. At the beginning, in order to bring mathematical analysis, a tractable analysis, they make these assumptions, which is people have a utility function on wealth, and this can be referred to as the Bernoulli utility function. And then you will have the von Neumann utility function, which is the expected utility. The point is that this expected utility function behaves as a utility function in itself, because it's a linear combination, right? If we have like a lottery, we have outcome 1, outcome 2, outcome n. If one with probability pi 1, probability pi 2, pi n, then the expected utility will be the sum, the weighted sum, with those probabilities of the Bernoulli utility associated with any of those probabilities. But the point is that this function, you see, you fix the probabilities, this is a function, has the characteristics of a utility function itself. And that depends on the characteristics of this first utility. So for instance, if that utility function has a first order positive derivative, a positive first order derivative, then the Bernoulli utility function, so the expected value of u when we construct the derivative with respect to the input, this will be positive as well, because this is the weighted sum with probabilities of the marginal utility functions. These guys are positive. We are making a weighted sum of positive things where the weights are probabilities, so those are positive amounts. So all these things will be positive. If this guy does not have a positive utility function and is negative, then the derivative of the expected utility function will be negative as well. And the same thing for the second derivative. The second derivative of the expected utility function is going to be negative if this utility function upon which we are building the expectation has a second order derivative that is negative as well. Why? Because we are taking once again a weighted average of the expectations. You construct the derivative of this thing, you get the sum of weighted derivatives, and that will give you something that must be negative if this guy here is negative. So, for Neumann theory, does not assume necessarily that you are risk averse. For Neumann theory, assumes that you have an underlying utility function u, whatever that is. So you can be risk neutral, you can be risk lower, you can be risk adverse. But the point is, you will make your decisions based on the expectation of the utility. And this is a function, right? This is in itself a function of wealth that has the same, that inherits the characteristics of the underlying utility function. If you were a risk lover, your expected utility function would be one that can be identified as risk loving. If you are risk averse, your expected utility function inherits those traits, and then you will be risk lover. Sorry, risk adverse. And then it comes this crucial definition. So what is risk adverse? Risk adverse is a guy that dislikes risk, and we can characterize that in different terms. You will have a utility function, an expected utility function, that would be concave. The utility function will be characterized as concave, but concave is for us the representative agent, right? So the representative agent will be just having this utility function, which is meant to capture this behavior. Remember, more wealth makes me happier, but at the same time, I have this marginal decreasing utility. So when I eat a little bit and it was starving, that makes me super happy. But when I eat and I already starved, that extra amount of food makes me happy, but not that much as at the beginning when I was really starved. So these traits match with the behavior that we call risk aversion. And risk aversion can be characterized also in terms of, again, a guy that will refuse to participate in a fair game, demanding a risk premium. You dislike risk. Because right now sounds like a Chinese, sorry, I said that. That's a Spanish expression to mean something sounds strange. Something maybe it's not, we will explain those terms because those concepts are fundamental for us. A risk adverse guy dislikes risk, and because he dislikes risk, he will be willing to pay something in order to avoid risk. And that amount is called the risk premium. So let me formalize these ideas, and because they are ideas that we need to formalize mathematically, I'm going to introduce certain concepts. This slide is a picture that I took 3 years ago when I was coming to teach the course, and this is from the airport in Alicante, in my hometown. The idea is that when you have increasing utility function, so a function, a utility function that has first order derivative, this condition, this makes possible what we call, remember the other day that we were talking about risk neutral valuation? I said the condition to identify the probabilities of the risk neutral valuation is that there should not be arbitrage opportunities. There should not be the opportunity of a free lunch. This thing, this kind of behavior that makes us love the free lunch, and that removes, that establishes a sort of equilibrium prices, a system of reference of equilibrium in the market, that we call absence of arbitrage opportunities, is enrooted in this trait. The fact that the utility function is increasing suffices to claim that there are no arbitrage opportunities in the market. When you have a market in which investors have a utility function which is increasing, these guys will behave in such a way that prices needs to have a relationship preventing opportunity of arbitrage opportunities. And that, I took this picture to show that. I took that picture at 8 in the morning, 7:30 in the morning in Alicante. That was this stand, and they were offering free capsules of coffee at 7:30 in the morning. How many capsules of coffee do you see there? At 7:30 in the morning. Zero. Why? Because it has the magic word, free. And that makes us behave in a particular predictable way. You are given something for free, and it's like a pum, in our brain it's like the free lunch, the opportunity. Because we sort of are the descendants of scavengers, right? The chance of eating for free, for us is like a wow. And you realize that. I can take 6, and if I can have 8, I will take 8 better than 7, and 7 better than 6, and no association when it comes for free. This principle operates in the stock market. and aligns prices in such a way that opportunities like this cannot exist for longer, and that puts pressure in supply and demand, and that puts pressure and defines prices. And we use this principle to value derivatives. There is neutral priorities, remember this expectation under the Q. That thing occurs because individuals have an increasing marginal utility function. That makes, an increasing utility function that makes this type of behavior. All right, let me formalize the idea that we are discussing here. So first of all, what is a fair game in economics? A fair game is a random game. It's a random game, and it's what we call the shock. Fair game in economics, shock in econometrics. It's a random variable, so let's call it epsilon, and I'm putting just two conditions on epsilon. I want epsilon to be a random variable, and this epsilon is going to have zero expectation. So you can go up or down, and you are bringing noise to the result. And it's fair because you cannot expect a gain nor a loss. Nor a loss. So zero expectation. And I want this guy, so the variance of epsilon is going to be the expectation of epsilon squared, the expectation of the second order moment, minus the expectation of epsilon squared, because the expectation of epsilon is zero, the expectation of epsilon squared is zero as well. So the variance matches the expectation of the second order moment, and this guy is going to be a certain amount that we are going to call sigma squared. Sigma squared is going to be positive and 5. So these are the conditions of a fair game. I want something to have zero mean, constant variance. Dispersion, you will center at 0, and you will be deviating from 0 like this. So low dispersion means low uncertainty, low risk, or you may have a very large value of sigma, and that means greater dispersion around 0. In both cases we are setting at 0, and you have greater scale, that means more variance. So this is the fair game. This is the shock, and this is a central piece in our models. Whenever you run an econometric model, we will say something like YT depends on alpha and XT, that's what you predict, that's what you expect, and then you add the shock. Something like this. And this is what this aligns everything. This is how we recognize reasoning economics by introducing random shocks. Alright, so the simplest fair game, the simplest shock, is one that is going to give you, let's say, minus C and C. This is the simplest thing, right? At this random variable, taking just two values. So let's say minus C and C, having it with the same probability. Of course, you can decide more complicated random variables, having different structures, having different probabilities. The simplest one I can think of is this one. Just two values, symmetric probabilities, zero expectation. The expected value of epsilon is going to be 0, so here we have the random shock. The variance of epsilon will be the expected value of epsilon squared. So this is C squared, the sign doesn't matter. We take the same value with the different probabilities, but the sum will be 1. So we have that C characterizes the dispersion. The variance of this simple fair game is characterized by how much gain or loss you have there. 100 and minus 100 is less volatile than 1,000 and minus loss.
Could you please explain again how a fair game introduces a shock?
The shock, how we introduce the shock here?
Yeah.
In the context of economics, because you want to introduce randomness. And randomness in your models can have different forms. For us, typically in economic models, in econometric models, randomness is always modeled in these conditions. You have something that makes the real values to departure from the theoretical values, from the expected values of your model in an unpredictable way. And unpredictable for us is zero expectation. You have the same chances to go up than to go down, same chances to make errors above or below. So this is connected to the fair game. I cannot predict what is going to happen, and my expected wealth is something like what I have plus surprises. Surprises can be above or below, but set it as zero. I don't know. Because if you have a non-zero expectation, then we will have something to say. If you give me a shot that has a positive expectation, I want to play that game. On average, the more expectation sometimes is confused, right? We will see that in the samples in the theory today. You will have to go, and it's a finite collection of outcomes. It's either minus C or C. So when you see zero expectation, what it means? It means that if you play many times this game, you will end up with zero. Sometimes I gain, sometimes I lose. On average, I will end up in around zero. Of course, if I just play one game, it's going to be C or minus C the outcome. But the zero expectation means that imagine yourself playing this game many times. You will be in a kind of neutral position. So you have, like on average, you lose nothing, you gain nothing. A risk adverse individual is someone that dislikes this game. You have, on average, nothing to lose, nothing to gain, and yet you dislike it. If you dislike this game, you are said to be risk adverse.
So the expectation being zero means that it's random, right? Fair game.
Exactly. The point is, you will say, because I have zero expectation, I should be kind of hawkish, right? It's like I don't care, maybe you give me 1,000, if we get we toss a coin, 50% 1,000, 50% I lose 1,000, it should be okay with that, right? If you are okay with that, you feel indifference to that, you are risk neutral. If you are willing to participate up to the point of paying for this game, then you are risk over. And if you dislike this game, say no, I don't want to play that game. It feels unfair to me, then you are risk over. So we can categorize people in 3 dimensions according to your attitudes to this game. If you feel indifference to this game, you are risk neutral. If you like this game up to the point of paying or playing in a game that has zero expectation, then you are risk over. And if you dislike this game, meaning I don't want to play this game, then you are risk adverse. Okay? So we are explaining how that is related to utility function and why it's like that, and why a guy that is risk adverse will dislike this game. There we go. So this is the identification that we do. Risk aversion is someone that has concave expected, or you just have utility function, it's the same thing, right? At the end of the day, as we discussed before. So someone has concave expected utility function, and hence someone that dislikes the fair game. And that guy, if he's confronted with a fair game, will be willing to pay to avoid the shot, right? We call it fair game, we can call it as well a shot. You are shocked and you tell me with 50% chance I'm gonna gain that much, and with 50% I lose the same amount of money, I dislike that thing. And because I dislike it, I'm willing to pay to avoid this shock. I don't want to play the game, and actually, I'm willing to pay to avoid the game. And the amount that you are willing to pay is called risk premium. You are willing to pay a risk premium. Risk neutrality. These neutral preferences, aversion, this aversion is characterized by concavity. As a question, Cindy?
Yeah, saying that the person would have to be paid to participate in the card game is the same as saying that they will be, no, saying that, wait, what did we say? That you have to, they are willing to pay to not participate, right? Is the same as
But
saying-
the game is not the same as before. The difference with the previous game
Yeah.
is that the previous game is not a fair game. It has it offers a positive expectation.
Yeah.
So because it offers a positive expectation, it's fair to pay something for it. Here is a game which is pure game in the sense that you don't have an unexpected game
So they are willing to pay to avoid.
to avoid it. And why? Because you dislike risk. What is the characteristic of this game? It has zero expectation. What is the characteristic? It shocks your wealth. And if you are risk-averse, you will be willing to pay to avoid that shock. A risk-neutral guy is someone who has a linear expected utility function. It's not concave, it's linear. Linear expected utility function. That guy is kind of neutral to a fair game. So for him it's okay. He will be willing to pay. And for that guy, the risk premium, so the amount that he will be willing to pay to avoid the game is zero. I'm not willing to pay to participate nor to avoid it. I feel neutral. I feel indifferent to that. It's something which is not meaningful to me. So that's why you are risk neutral. This game, the characteristic of this game is randomness. It's the variance. It's not the mean. The mean is zero. It's just the fact that it's shocking your current initial state of wealth. So you feel okay with that. And the third guy, the third type of attitude is the risk-loving. Risk-loving attitude is one that has a convex expected utility function. This guy likes the game, likes the fair game, and he likes a game, remember, that has zero expectation. So he likes the game because he finds pleasure in the variability. He finds pleasure in risk itself. We like wealth, but this game is not giving you a expected level of wealth. It's bringing you noise.
For the neutral one, you say risk premium equals 0, and then you say it still pays risk premium.
This guy is willing to pay a certain amount, and this risk premium for the risk averse guy is going to be positive. It's an insurance.
And for the neutral guy,
For the neutral guys, the risk premium is 0. And for the risk-loving guy, the risk premium is going to be negative. He is willing to pay for the pleasure of playing the game. This guy is willing to pay to avoid the game. This game doesn't care at all. He will not pay neither for taking the game nor avoiding. And the risk-loving guy will pay for taking the game. Is okay? So someone paying for an insurance is who?
The risk averse.
The insurance company is what? Hmm? The insurance company is what?
In the context of
In this context,
Islam,
people are divided in everyone that you know falls into one of these three categories.
Risk.
That will be the risk lover. And someone who doesn't care about, I go without insurance, that guy is risk neutral. Okay, we see it. Of course, there is a deeper nature when you think about the insurance company being risk lower. The point is that these guys take the risk and then put the risk out in the company. They have methods to diversify the risk. They don't take it. If they take the risk on the exchange of money, they are risk lowers. Someone who pays to go into a roller coaster is risk lower. Okay? Someone who will go only into a roller coaster is being paid risk averse. Okay, guys, let's take 20 minutes. 20 minutes break, and we formalize all these ideas. This is super important for us. Everyone that you know, according to the expected utility theory, falls into one of these three categories.
That's the expectation of epsilon equals 0, right?
What?
The expectation
On the short epsilon, 0.
Pero no es como la política, pero no es la pizarra.